Sometimes the simplest looking puzzles hold the deepest secrets. What if I told you that this little object, these nested boxes, could actually unlock a huge mathematical idea? An idea that shows up everywhere, from nature to computer code. Well, today we're going to take that journey from a physical toy all the way to the elegant, infinite world of algebra. Okay, so let's start right here. It looks pretty straightforward, right? It's a box inside another box, and so on. But the real question, the one we're going to crack today, is staring us right in the face. Just how many of those tiny little blocks does it take to build each one of these colorful layers? So to figure that out, we've got to get to know our puzzle a little better. Let's break down this cube within a cube and see how it's actually built on a surprisingly simple repeating idea. This really shows it perfectly. The best way to think about this is like one of those classic Russian Matryoshka dolls. You've got a whole series of cubes, and each one is made to fit just right, perfectly snug, inside the next biggest one. It's just a really neat piece of geometric design. Now let's get specific with the sizes. The big one on the outside, the orange cube, is a 7 by 7 by 7 grid. Nestled inside that is a 5 by 5 by 5 gray cube, then a 3 by 3 by 3 pink one, all the way down to that single little red cube in the middle. See the pattern? 7, 5, 3, 1. Each cube's side is just 2 units smaller than the last. That simple little rule is going to be the key to everything. So, we've got the physical shape down. Now, let's switch gears and translate that geometry into the language of numbers. Let's talk about volume. And that leads us to our first big question. As we go from that tiny red block at the center and move outwards, how quickly does the total number of blocks grow? And let me tell you, it's not some nice, steady little climb. So for that big orange 7 by 7 by 7 cube, you do the math, 7 cubed, and you get a whopping 343 little unit cubes in total. The gray cube just inside that one, that's 5 cubed, for volume of 125. And the pink one, 3 cubed. That gives us 27 blocks. And of course, at the very heart of it all, our little red cube is just 1. I mean, look at those jumps. From 1 to 27 to 125, all the way to 343. That really shows you the incredible power of cubic growth. It's explosive. All right, so we know the volumes of the solid cubes, but now it's time for the main event. Let's figure out how many blocks are in just one of those hollow outer layers, or what we'll call a shell. Okay, so how on earth do we count all the little blocks in just that orange shell? Well, there's a really clever shortcut. Instead of trying to count every single block one by one, which would take forever, we can just take the total volume of the big orange cube and subtract the volume of the gray cube that's sitting inside it. Simple. And here's the math laid out for us. We're starting with the 343 blocks of the full orange cube, and we're just taking away the 125 blocks that make up the gray one. Whatever's left over, well, that has to be the shell, right? And there it is, 218. That is the exact number of little cubes it takes to build that hollow orange layer. So satisfying to get a nice, clean answer like that. Now, solving one problem is great, but what if our cube was, I don't know, an 11 by 11 or a 99 by 99? This is where we level up and we move from just doing arithmetic to finding a universal shortcut with algebra. And here it is, the secret code. For any outer cube, let's just say its edge length is n, the cube right inside it will always have an edge of n minus 2, remember? So the formula for any shell is simply the volume of the big cube, that's n cubed, minus the volume of the one inside it, which is n minus 2 cubed. This one little formula works for any size cube in our pattern. But the really beautiful thing about math is that there's usually more than one way to get to the right answer. That subtraction method is super elegant, but there's a totally different way to attack this problem. So instead of subtracting, you could actually try to build the number up. You could start by counting all the cubes on the 6 outer faces. But you'd immediately hit a snag. As you can see, you'd end up counting the cubes along the edges twice, and the corner cubes would get counted 3 times. So then you'd have to go back and carefully subtract all those overlaps to get to the right answer. It's definitely more complicated, but it's another totally valid way to solve the puzzle. So we've gone from a physical object to its numbers and even to an algebraic formula. Now let's just zoom all the way out and look at the big, beautiful idea that ties us all together. You see, this whole thing, this entire cube in a cube puzzle, is a physical model of a powerful concept called recursion. And all recursion really is the idea of a process that repeats itself, where each new step is built on the step that came right before it. That simple rule we're talking about here is just take a cube and put a smaller one inside it that's 2 units shorter on each side. You apply that rule to the 7 cube to make the 5 cube. You use the exact same rule again to get the 3 cube, and again for the 1 cube. It's one simple instruction, just repeated over and over to create this whole complex thing. Now, our physical toy here, it obviously has to stop. It has a beginning and an end. But in the abstract world of math, that pattern, that recursive rule, doesn't have to stop. You can imagine a 9 cube with a 7 cube inside, an 11 cube with a 9 cube inside. You could just keep going. What if that pattern never had to end? It's a pretty wild thought, and it takes us from a simple puzzle box all the way to the edge of infinity.